Welcome to the second video of the compressible flow chapter. We are going to learn an important reference state called the stagnation state and start studying isentropic flows inside ducts. Consider compressible flow inside a duct with variable cross-sectional area, similar to the one shown here, but not necessarily in this shape. Flow and fluid properties in this duct, such as density, pressure, speed, or temperature, may change mainly because the cross-sectional area changes, there can be frictional effects, or there can be heat transfer. If we neglect the last two of these and only consider the effect of the variable cross-sectional area, what we are left with becomes an isentropic flow. In such an idealized flow, entropy remains constant and the analysis simplifies. Although idealized, we can learn a lot by studying such a flow. The flow will be assumed to be one-dimensional, with the velocity field being purely axial, and all properties will be taken as constant at any cross-section. Consider two sections, shown here as 1 and 2, in a one-dimensional flow inside a duct. Here we see the conservation of energy equation written between these two sections. On the left-hand side, we have the heat and the work interactions with the surrounding. We will consider them to be negligible. On the right-hand side, there are enthalpy, kinetic energy, and potential energy terms. Considering negligible potential energy change between the two sections, which is usually the case for gas flows, the energy equation simplifies to the one shown at the bottom of the slide. What we are left with is the balance of enthalpy and the kinetic energy terms. H plus V squared over 2 is known as the stagnation enthalpy. Therefore, this equation says that in this isentropic flow, stagnation enthalpy stays constant. Actually, it's important to note that this equation is valid for adiabatic flows, that is, flows with no heat transfer, because this is the only major assumption we used in obtaining it. Isentropic flow further assumes no friction, which is not a necessary condition to derive this equation. Make sure that this point is clear before proceeding further, because we will make use of this fact later. Stagnation properties are shown with subscript 0, indicating that at the stagnation state velocity is 0. Here you see the simplified energy conservation equation written in terms of the stagnation enthalpy H0. This equation, stating that H plus V squared over 2 is constant along the duct, is similar to the Bernoulli equation that we used frequently for incompressible flows. To see the similarity better, we can write the enthalpy as internal energy plus P over rho. In this form, it looks like that we have an extra internal energy term in the Bernoulli equation that we are familiar with. We will come back to this similarity later. Stagnation enthalpy is called stagnation because it's the enthalpy of the stagnation state where the velocity is 0. We can think of the stagnation state as the state of a large reservoir which is used to feed the flow in the duct. Velocity in this large reservoir is negligible, and the properties of the gas here are the stagnation properties, such as the stagnation pressure, stagnation temperature, or stagnation enthalpy. Stagnation state is an important reference state for us. Even if there is no such stagnation reservoir feeding the duct, we can still think of a hypothetical stagnation state and make use of its properties in our calculations. In this slide, we emphasize the fact that in an isentropic flow, the stagnation state is unique. If we take the fluid at state 1 and decelerate it isentropically to 0 speed, we end up at the stagnation state. If we do this for state 2, we again end up with the same stagnation state. Here is what this isentropic deceleration looks like on the enthalpy-entropy diagram. The black circle shows any state inside the duct. No subscript is used for it to make it general. During the isentropic deceleration, shown with the blue line, entropy remains constant and enthalpy increases to H0. According to the conservation of energy, the increase in enthalpy is v²/2, where v is the initial speed. After defining the stagnation state as a reference state and understanding the energy conservation for an adiabatic flow, we can derive the relations shown in this slide, which provide the ratio of the temperature, pressure, and density of any state to the properties of the stagnation state. As you see, these ratios are only a function of the Mach number and the specific heat ratio K. If we know the stagnation state properties, then we can calculate the properties at any state only by knowing its Mach number. The solution of this exercise is given in the solved examples handout. It is important to note that the temperature ratio equation is valid for any adiabatic flow of a perfect gas. But the pressure and density ratio equations require isentropic flow assumption, that is, adiabatic plus frictionless. You do not need to memorize these equations, but you need to know how they are derived. To make more sense of them, we can plot them for a gas with a given specific heat ratio. The plot seen here shows these relations as a function of Mach number for air, with K being 1.4. Mach number 0 corresponds to 0 speed, and the ratios are equal to 1. As the Mach number increases, the ratios drop smoothly. As an example, consider a duct attached to a stagnation reservoir. Depending on the exit conditions, a certain flow will be established inside the duct. Let's say that there is a cross-section where the Mach number becomes 1, that is, the speed becomes the speed of sound. According to this graph, pressure at that section is equal to about half of the stagnation pressure. Density is about 60% of the stagnation density, and temperature is about 80% of the stagnation temperature. More precise values can be calculated using the equations rather than the graph. It is also possible to tabulate the data on this plot, which is actually used more commonly than the equations or the plot itself. We will see such tables in the coming slides. The first exercise of this slide is about the calculation of the temperature rise at the tip of the Pitot tube of an airplane, which travels at 900 km per hour. Here is the schematic and the solution of this problem. According to a passenger on the aircraft, the Pitot tube is static and an upstream flow is approaching it at a speed of 900 km per hour. Tip of the Pitot tube is a stagnation point and the velocity there is 0. We are asked to calculate the temperature of this point. We can make use of the adiabatic energy conservation equation, writing it first in the form of an enthalpy difference, and then converting the enthalpy difference into a temperature difference by using an extra specific heat Cp. The required temperature rise can be calculated as 31 degrees Celsius. With this temperature rise, the minus 60 degrees Celsius air will become minus 29 degrees Celsius. This is still a very low temperature, and Pitot tubes usually have heaters to avoid freezing and the formation of ice. Note that this problem could also be solved directly using the temperature ratio equation of the previous slide, which is also shown here. For this, we first need to calculate the speed of sound at minus 60 degrees Celsius and then the Mach number corresponding to 900 km per hour. Using this Mach number together with the specific heat ratio of air, we can use this equation to arrive at the answer. Please try to solve the problem in this way and see if you can get the same answer or not. As seen here, Deceleration of air causes heating, and the temperature rise is proportional with the square of the speed. For very high speeds, this temperature rise can be very severe. The reading assignment shown here is about this. It is related to the thermal protection systems of space vehicles. And this figure shows how the supersonic passenger aircraft Concorde heats up as it flies at Mach number 2. The highest temperature of 127 degrees Celsius is seen at its nose as the Mach 2 flow decelerates to stagnation. The second exercise of this slide makes use of the same principles as the first one. Please work on it by yourself. Exercise of the next slide is about the comparison of the variation of the stagnation pressure over static pressure ratio with Mach number obtained in two different ways. The blue curve is directly coming from slide 421. It is the plot of this equation with the specific heat ratio taken as 1.4. The red dashed curve is obtained using the incompressible Bernoulli equation. It is the plot of this equation shown in red color, which is derived in the handout. As seen in the plot, these two relations predict almost the same ratio for Mach numbers less than 0.5. To be more specific, up to Mach number 0.45, the difference between the curves is less than 5%. As the Mach number increases, the compressibility effects become more and more important, and the curves start to deviate from each other. The exercise of the next slide is an important one. It is about deriving relations for the change of pressure and the change of velocity with the change of cross-sectional area for isentropic flow inside the duct. For this, we are asked to use a control volume of differential length dx. The properties at the exit of the control volume are only slightly different than the ones at the inlet. We want to derive relations for how dP and dV change with dA. These can be derived using the mass and momentum conservation principles. The solution of this exercise is available in the solved examples handout. Please study it carefully. Here are the results of the previous exercise. These are important relations in understanding the basics of flows with variable cross-sectional area. You do not need to memorize them, but you need to know how they are derived and also know how to interpret them, as we are going to do here. The important detail here is that in both equations, there is the 1 minus Mach number square term. Due to this term, the flow character becomes different when the flow is supersonic compared to the subsonic case. And also due to this term, the sonic flow with Mach number 1 is a very special one. 4 possible cases are shown in this table. In the first one, dA is positive, meaning that the duct cross-sectional area increases in the flow direction. And the Mach number is less than 1, that is, the flow is subsonic. When we use these in the above equations, we get a positive dP and a negative dV. Velocity decreases in the flow direction and pressure increases. These are parallel to our knowledge for incompressible flows. This device is known as a subsonic diffuser. Diffuser is the name given to devices where the fluid decelerates. In the second case, dA is negative. Mach number is still less than 1. According to the above equations, pressure decreases and velocity increases in the flow direction. This is again similar to what we would have in an incompressible flow. This device is called the subsonic nozzle. Nozzle is the name given to devices where the fluid accelerates. To summarize, these two subsonic flow devices are behaving as we expect. In other words, they work similar to how an incompressible flow device would work. But things get strange when the flow becomes supersonic. The next case is for supersonic flow with decreasing cross-sectional area. For this case, pressure increases and velocity decreases in the flow direction, which is strange. As area decreases in the flow direction, velocity also decreases. This device is a supersonic diffuser. Interestingly, if you want to slow down a supersonic flow, you need to use a converging duct, not a diverging one. This is just the opposite of our prior incompressible flow knowledge. And the final case is for supersonic flow with positive dA. This results in negative dP and positive dV. This is again strange because it says that to accelerate a supersonic flow, we should use a diverging duct, not a converging one. This device is a supersonic nozzle. To summarize, supersonic flow devices look just the opposite of subsonic ones. Supersonic diffuser looks like a subsonic nozzle, and supersonic nozzle looks like a subsonic diffuser. In supersonic devices, the way pressure and velocity changes with area is just the opposite of what we previously experienced with incompressible flows. Although pressure and velocity change with area in an unexpected way, the fact that pressure increases as velocity decreases and vice versa is still true. And what about the sonic flow case, where the Mach number is unity? In both of the equations, the right-hand sides become 0 when the Mach number is 1. This means that the left-hand sides should also be 0, which can happen if dA is 0, that is, the cross-sectional area goes through a minimum. We will discuss this special sonic flow case more in the next slide. To satisfy the conservation of mass and linear momentum principles, the sonic flow can occur in a duct only when dA is 0. This can happen only when the cross-sectional area goes through a minimum, as shown in this figure. Sonic flow can occur at the throat of this converging diverging duct. It is important to understand that the flow is not necessarily sonic at the throat. What we are saying is that if sonic flow occurs in this duct, it can occur only at the throat. It is quite possible that the flow is totally subsonic or totally supersonic everywhere in this duct, with sonic flow seen nowhere. Examples of these are sketched here. In the first duct, subsonic flow at Mach number 0.2 enters the duct. It accelerates up to Mach number 0.7 at the throat, and decelerates in the diverging part, exiting the duct at Mach number 0.3. The flow is subsonic everywhere in this duct. In the second example, supersonic flow at Mach number 2 enters the duct. It decelerates down to Mach number 1.5 at the throat, and it accelerates in the diverging part, exiting as supersonic. What determines whether there will be sonic flow at the throat or not is the nozzle shape and the inlet and outlet conditions, such as the pressures. We will talk about the details of these later. One question that you may ask is, what about the cross-sectional area being a maximum instead of minimum, such as the one shown here? Can sonic flow be seen in that case? The answer is no. Think about this possibility and, using the table of the previous slide, show yourself why sonic flow cannot happen in such a duct. You can get help from your textbook if you need. As an extreme case, sonic flow can also be seen at the exit of a duct. The first case here is a subsonic nozzle, with Mach number being less than 1. Flow accelerates in this device, and it can just happen that the Mach number at the exit becomes unity. It's not necessarily the case, but it can happen. Similarly, in the second case, which is a supersonic diffuser, the flow decelerates, and it can just happen that the flow at the exit is sonic. But these are two extreme cases, and when we think of sonic flow inside a duct, we typically consider the throat of a converging diverging duct, not these. The exercise in this slide is about the converging-diverging duct we have seen in the previous slide. It claims that this duct is the only device that can accelerate a gas from subsonic to supersonic speeds, or decelerate a gas from supersonic to subsonic speeds. This claim can be proved directly by looking at the table of slide 425. In the first possibility, subsonic flow enters the duct. The converging part of the duct accelerates this flow all the way to sonic speed at the throat, acting as a subsonic nozzle, and the second part acts as a supersonic nozzle, further accelerating the sonic flow to supersonic speeds. At the exit, the flow is supersonic. This device is a combination of a subsonic nozzle and a supersonic nozzle. It is called a converging-diverging nozzle, or the de Lava nozzle, in the honor of the Swedish inventor Gustav de Lava, who invented it in 1888. This nozzle is used in most modern rocket engines, supersonic jet engines, and some types of steam turbines. Here is the RS-25 engine of the Space Shuttle, which carried American astronauts to the International Space Station for 30 years, and in the near future, its advanced version will be used in Moon and Mars missions. Its nozzle is the Lava type, and the diverging part of it can clearly be seen in this figure. Let's watch a short, non-technical video about it.
So, exactly what is the RS-25 engine? For 3 decades, the RS-25 helped propel the Space Shuttle into orbit. This amazing engine will now be part of NASA's Space Launch System, which will be the most powerful rocket ever built, and will carry our astronauts to the Moon and eventually to Mars. NASA has 16 RS-25s, and each SLS rocket will have 4 engines. These engines have been modified and upgraded for their bold new mission, and are being tested at NASA's Stennis Space Center. These engines are big, really big. The RS-25 is 14 feet tall and 8 feet in diameter. That is about the size and weight of a compact car, or 2 F-15 jet engines, and produces 8 times more thrust. Along with the 2 solid rocket boosters, the RS-25 engines will power the SLS at speeds of 17,500 miles per hour. That's 73 times faster than an Indy 500 race car.
And here is the Merlin engine, designed by Spacex. Its de Lava nozzle can clearly be seen. Let's watch an actual firing of this engine to feel how powerful it is. We are back at slide 427. In the second possibility mentioned in this slide, supersonic flow enters the duct. The converging part of the duct decelerates this flow all the way to sonic speed at the throat, acting as a supersonic diffuser, and the second part acts as a subsonic diffuser, further decelerating the sonic flow to subsonic speeds. At the exit, the flow is subsonic. This device is a combination of a supersonic and a subsonic diffuser. Therefore, it is not proper to call it a de Lava nozzle. Compared to the first possibility mentioned earlier, its use is less common in engineering applications. This is the end of the second part of the compressible flow chapter.